Excellent. Okay, so I hope Google YouTube audience can hear me, and I have a pleasure to introduce our next invited speaker. It's Tomasz Malisiewicz, and I'm quite sure I pronounced that right. And Tomasz did his PhD at CMU and has now close to 15 years experience in computer vision, I guess, in robotics. So he also worked at MIT, set up his company, Vision AI, and now works for Magic Leap as a principal engineer. He's very well known for his recent work on SLAM and combinations with deep learning, as well as 3D reconstruction. So I'm really excited and looking forward to your talk, Tomasz. So over to you then.
All right, Christian, thanks for the warm introduction. So I'll say again, my name is Tomasz Malisiewicz, and the title of my talk today will be Deep Visual SLAM Front Ends, SuperPoint, Superglue, and Supermaps. Now, for those of you turning in on YouTube, this talk is being delivered at the joined workshop on long-term visual localization, visual odometry, and geometric and learning-based SLAM at CVPR 2020. Let's first take a look at some of the problems that can benefit from advances in visual SLAM. In the first row, we see mixed reality applications. Those are consumer devices that you wear on your head, and they have to localize themselves in space, and they enable a next generation of experiences by blending digital items together with physical real-world items. In the second two rows, we see robotic applications, such as self-driving vehicles and autonomous carts. In all of these problems, cameras are heavily used to make sense of the world around you. And that's the crux of the visual SLAM problem. In today's talk, I'll be talking about three different things. First, I'll talk about SuperPoint, and that is my team's attempt to bring convolutional neural networks into the world of deep learning. Next, I'll talk about Superglue. That's very recent work that we will be disseminating at this year's CVPR. That's about using graph neural networks and attention to further improve the correspondence or the feature matching problem. And then finally, I'll talk about supermaps. Those are just some ideas on how we can move beyond pairwise matching and finally fulfill this dream of end-to-end deep visual SLAM. Let's begin with the first part about SuperPoint. Visual SLAM can be decomposed into two parts. First, there's the front end, whose job is to extract features and associate them. And then the second part is the back end, whose job is to take 2D quantities and upgrade them to 3D. Now, the front end deals with image inputs, and it makes sense to use convolutional neural networks here because we've seen lots of successes when we had to apply convnets directly to images for classification and object detection. And in this case, the back end will be an optimization procedure. And the optimization is typically done over poses and map quantities. This is done by solving nonlinear least squares problems. It's typically known as the bundle adjustment procedure. So let's take a look at how we tackled first the front end problem of visual SLAM. We introduced a network called SuperPoint. SuperPoint is just a code name for this simple network. It's a convnet that has two different kinds of outputs, the keypoint 2D locations and the keypoint descriptors. It's a powerful, fully convolutional design. Everything is standard vanilla deep learning components. The points and descriptors are computed jointly. It's important to note here that unlike earlier systems, you don't have to first extract interest points, then crop little patches around them, and then send them to a machine learning system. Everything here is done directly by the convolutions inside the network. We used a VGG-like backbone for our experiments in order to make it not too big, but there's no reason why you can't take today's most recent backbones and even modernize this approach. We designed SuperPoint for real-time processing with the GPU. That means we did not on purpose make our backbone very large. We wanted to make sure that this can go into real-world products. We designed the system so that the key point description and the location estimation share most of the weights. 90% or more of the computation is shared by the standard backbone. And we used sparse outputs so that this system can be used inside something that is fit into embedded computers. So yeah, here the front end will be the SuperPoint, and the back end that we'll use later will be some other geometric module. Very quickly, I want to point out that the reason why this works is because the key point or the interest point decoder performs a classification problem. We realized that the goal of this network will be to just classify which pixel is interesting and which one isn't. We made the assumption that within an 8x8 pixel neighborhood, there can only be one interest point. So for the 8x8 patch, that corresponds to 64 possible locations and a dustbin. Those are 65 values. So the goal is to create a distribution over those 65 values. The benefit about using distributions here is that we can then reshape everything and we get nice heat maps. So let's now look at the question of how do you train such a SuperPoint network? Remember, now the goal is to go from images to keypoint locations and descriptors. The training is relatively straightforward. We designed our system to work on a large collection of image pairs, where here are image pairs where one image sampled from a data set and then warped by a homography. By warping images with a homography, we know exactly where the pixels go. So the correspondence is then known. So training the descriptors is relatively easy via modern metric learning techniques. We use the contrastive loss in this case. The remaining question is, where do the key points come from? If we know where the key points are in one image, with the homography warp, we know where they go in the second image. But where do we get these points initially? If we take images as the ones I'm showing on the slide and you send them on Mechanical Turk to other countries and ask people to label interest points, you will get answers all over the place. The reason is because the idea of an interest point is not something that exists in reality. It's a convenient creation that we engineers and scientists created to cope with the image matching problem. But this is too hard to have humans label. It's nearly impossible. So we devised a self-supervised training procedure that would allow us to bypass this problem. So the goal is to first train something on a simpler world, one where we can define what things are interesting and which things aren't. We use a world of synthetic shapes, where we use a non-photorealistic renderer with lots of noise, and then the corners in this world are interesting points. After we've trained on our synthetic shapes, the goal is to transfer this information to a real data set of images. Here we use the MS-COCO data set, and the MS-COCO data set has no interest point labels. So we invented a procedure called homographic adaptation. Homographic adaptation lets us first train on one data set and then transfer results to the second data set. Here are just some examples of some more of the synthetic images that we sort of train on. Notice there's nothing fancy here. This is not an OpenGL renderer. This is something very simple where you have 2D rendering programs that can be used to show the shapes. Our earlier part of SuperPoint was just the interest point detection bit, and we called that magic point. Our earlier experiments comparing magic point to other well-known techniques like FAST, Harris, and Xi interest point detectors showed a big performance gap, particularly when the images are affected by lots of noise or they're darkened. Let's now take a look at the homographic adaptation procedure and see how it works. The goal is to simulate planar camera motion using homographies. This is a self-labeling technique that can be used to suppress spurious detections and enhance repeatable points. You might think that you can just run at the detector, the magic point, save the output, and use that for training. And that's generally not good enough. So let's see how homographic adaptation works with this following illustration. We start with an unlabeled input image. We then synthetically warp the image, create different homographies, and then we run the interest point detector on each version of the image. This gives us multiple different sets of detections. We then warp them back and aggregate them to create a superset of detections. The reason why we called our final system SuperPoint is that this homographic adaptation procedure allowed us to generate a superset of magic points. So SuperPoints for us are a superset of what we could get with an earlier technique. Let's take a look at some examples of what it looks like to run SuperPoint on a pair of images. In this example, SuperPoint is in the top left, and the green lines show correct correspondences. In the top right, we see Lift. That's another deep learning-based system, slightly predating SuperPoint. In the bottom left, we see SIFT, which is one of the most well-known local feature matching methods. And in the bottom right, we see Orb. Notice that SuperPoint has the largest density of green matches in this example. Also note that in this particular pair, the Orb tends to not have many detections, and it seems to have many that are clustering around the small number of high feature reach regions. This is not good if your goal was to later estimate a relative pose between the images. You would like to have points that are detected around the entire image. Here's another example that also shows a nice density of points being able to be aligned by SuperPoint. And also it shows the deficiency in Orb by focusing too much on texture-rich regions. In this last example, we see a different relative rotation between the images, and we see Lift, the other deep learning-based system, struggling. In this case, SuperPoint works. But I want to let everybody know that based on the aggressiveness of the transforms, you get to train for this effect. If you use all possible rotations in your training, you lose a little bit of the power. The VGG backbone is not able to be fully rotation invariant. So we tend to train with about 15 to 30 degrees rotations maximum. But Lift here we see is not able to get enough matches. So far, everything has been 2D based. And you might wonder, will this 2D based training recipe work in the 3D world? What we did is we ran a simple connect the dots algorithm using nearest neighbor matching, and we applied SuperPoint to a large number of videos. We were pleasantly surprised to find SuperPoint working on lots and lots of different data sets. This was a nice benefit. These videos are showing the tracking mode of SuperPoint, where all of the correspondences are done in a frame-to-frame fashion and then stitched together very simply. We released our pre-trained SuperPoint network based on PyTorch with only 2 files, very easy to run. This came out in the first Deep Learning for Visual Slam workshop at CVPR 2018. We recommend people go to our GitHub page if they want to check out just the SuperPoint component. So now before I go and talk about kind of superglue and the more ambitious sort of project, let's very quickly study that robustness property of SuperPoint. We asked ourselves, can we apply SuperPoint to another task? Maybe one where we could highlight the robustness of SuperPoint. We decided to take a fiducial pattern, that is the Chirruco pattern. Chirruco pattern is an Ruco patterns embedded inside a chessboard. You can see this pattern in the left part of the slide. We took the exact SuperPoint architecture. The only modification is we replaced the descriptor, the real value descriptor, with now an ID classifier. In this case, our pattern has 16 different kinds of points that need to be detected. So this network has a 16-way classifier that chooses which of those points is being detected. We observed that this kind of training with data augmentation and this kind of architecture, when applied to this Chirruco pattern, allow the system to effectively see in the dark. Going from left to right, we see the images being darkened. The top row shows the raw image. The middle row shows the output of a classical OpenCV system for this Chirruco pattern. This classical system is relying on lots of image processing operations, and those operations break down as the images get darker. With the deep Chirruco system, you can see the detection of the interest points even when the images are so dark, a human can't decipher what's going on. So here are some videos showing this deep Chirruco system juxtaposed to the traditional OpenCV system. Every time the frame turns red, that means the system was not able to detect enough key points or there was some issue with the estimation. Notice that the deep Chirurco system is able to continue detecting the pattern even when there are strong cast shadows, when the lighting is sort of very low. And this is really an amazing property of using deep networks for local feature detection. Next, we wanted to see if SuperPoint can be improved if we train it with real sequences, real data, and use some kind of backend in the training loop. So this is going to be SuperPoint VO that I'll talk about in the next minute or two. If you take SuperPoint and you run a simple visual odometry backend, it's not that difficult to upgrade everything to 3D. Here's a very simple point cloud recovered from the Freiburg TUM RGBD dataset. Here's another simple example that shows what happens when you take the SuperPoint system and then you put it together with a VO into a reconstruction. We realize that the benefits of a VO-based SuperPoint training is that we can establish correspondences across time. We saw earlier that the SuperPoint tracker worked quite well, and this is what this training regime exploits. Also, using VO-based training allows us to determine which points are stable and which ones are not stable. So let's take a look at the VO-based training procedure for SuperPoint. We start with an input monocular sequence. We have the intrinsics for this sequence, but we do not have depths or poses. We run SuperPoint on this sequence on every frame. We do the correspondences. We get our point tracks. And then we perform in an offline fashion and upgrade to 3D. I guess in this case, you could just call this SFM. The difference between VO, SLAM, and SFM is less important as this is done offline. But after you upgrade everything to 3D, you get your labeled point tracks, and then this is the data you can use for training. So how can we define stability? When you get a point track, and then you upgrade it to 3D, you can look at the reprojection error. If the point has a low reprojection error that is less than 1 pixel, we call it stable. If the reprojection error is larger than 5 pixels, or some other large threshold, we say it's not stable. Otherwise, we ignore that stability classification during training. Here's an output of the labels on some video sequences. These are held out video sequences, and the colors depict the different stability labels. Green are stable points, red are unstable points, and black is this larger class of not entirely sure. Once you have these stability labels, training SuperPoint VO proceeds like the original system. We generate extra random homographies to create more difficult correspondences. And you have an architecture now that looks just like SuperPoint, but it was trained using sequences. Let's see how this performs compared to SuperPoint and other systems. We evaluated the SuperPoint VO system on a pose estimation task on ScanNet. The left plot will show the rotation error and the right the translation error. The higher you up on the plot, the better you're doing. The dotted blue line is our SuperPoint VO system. And the next two closest lines are SuperPoint, the original one trained on Coco. And we also ran an experiment. We trained our SuperPoint system just on ScanNet images without sequences. But when there is only 30 frame difference in our videos, this corresponds to 1 second of motion. There's only a small benefit in using VO. Very hard to tell apart which system is truly better. Was it really worth using VO just to get that small benefit? We repeated the experiment with a larger frame difference. Now, frame difference of 60 corresponds to approximately 2 seconds of motion. We start seeing now VO starts helping. And in the final experiment, we looked at the largest difference, that is frame difference of 90 frames corresponding to 3 seconds of motion. Now the gap between the VO-based training and the other methods is significantly larger. By doing these experiments, we realized that wide baseline matching is really what we should be after. If you're going to be tracking images that are just collected 1/30 of a second apart, you don't need lots of complexity there. Things tend to work quite well. When you have larger and larger differences between the images and the two images have smaller visual overlap, you need wider baseline matching. So now onto the second part, I'm going to talk about superglue. And superglue is our recent work on applying learning to the problem of finding correspondences. Superglue, learning feature matching with graph neural networks, is presented at this year's CVPR 2020. This is work that was done by Paul Edward Sarlin, Daniel Detone, myself, and Andrew Rabinowitz at Magic Leap. Paul is a PhD student at ETH Zurich, and he received his master's thesis for doing this work with my team at Magic Leap. Superglue is a graph neural network and an optimal transport procedure. Superglue is a system that uses SuperPoint and this extra mechanism to perform wide baseline matching. It works on image pairs, it works in real time using a GPU, and it gives us state-of-the-art results on both indoor and outdoor matching. Superglue can be trained to work with SIFT or with SuperPoint or just about any other system. A key thing to note here is that our goal was to design a matching system that would be better than motion-guided matching without any motion model. In our earlier work on integrating SuperPoint with SLAM fundamentals, we saw that motion-guided search does help a lot. However, when the motion estimate is bad, it can be catastrophic. We wanted to design a system that had no requirement to have a motion prior and was just trained on all of the hard stuff we could see in the world, and it just works without manually engineering little tricks. Superglue has two parts. The first is a graph neural network with attention. And the second part is the classical optimization procedure that we solved with the Sinkhorn algorithm. Superglue requires both sets of local features to go into the attention mechanism. This is very different than how we had previously thought about matching, where earlier we were designing networks to do all the processing for each image independently, and then only at the end do some kind of simplest nearest neighbor matching. Here, the SuperPoint outputs get fused with their locations in the Keypoint encoder. They go into one network that's solving the two image matching problem. It goes through many layers of attention, and the final descriptors are fused together into a partial assignment matrix using the Sinkhorn algorithm. These details will be discussed later at the CVPR. Let's take a look at some videos of SuperPoint and Superglue in action. These are some results on held out sequences from the ScanNet dataset. Notice in the top right, we have many, many more green lines showing correct matches than red ones. This is a very difficult sequence where the interest points on the floor have very similar descriptors, and SuperPoint has problems disambiguating which tile is matching to which other tile. We also repeated experiments with SuperPoint and Superglue on outdoor data, and we compared it against the best that we could find in terms of inlier classification, and also works extremely well. From the evaluation slide, the most important thing to take home is that SuperPoint and Superglue is the best recipe that we could find sort of today. If you look at this evaluation, you can also see in dark blue SIFT and Superglue. This is a different Superglue trained with SIFT, but it does seem to benefit the original SIFT. So if you're interested in training your own Superglue for your own input features, feel free to get in touch with the first author. Superglue is also released as a demo. You can go to the website, the project website, or directly to the GitHub page, and you can check out this repository. You can run this on a GPU laptop or a GPU desktop at about 15 frames per second for approximately 512 key points on a VGA-sized image. It's a pretty amazing demo. Now, rather than me showing you more empirical results, I want to give you a slight little snapshot of what it's going to look like if you get this code up and running. I ran some simple experiments last night just in my spare bedroom by moving checkerboards around occluding patterns, messing around with the camera focus. And in all cases, the demo continues to impress me. If you're a researcher yourself, I recommend you take a look at the paper, you look at our experiments, but all these things will take you 10, 20 minutes, hours to decipher everything. If you just get the demo up and running, get your webcam plugged in, point it at the world, try to break it, I think you will be impressed, because I was. So before I wrap up, I want to outline a little bit, what comes next. Now that we saw the front end, that features being replaced with SuperPoint, we saw superglue, another important mechanism for even getting better matches. What's next? So rather than describing how what next works, I want to describe at the high level desiderata. What do we really need to do to SuperPoint and superglue in order for it to become something like supermaps? So superglue works with a pair of images, and I believe it'll be important for us to think about alignments between sets of images. That is, when you have a map of the world collected as a sequence of keyframes, how can you then align a new incoming image to this set of images? Or how can you align two different maps that were built? That is, aligning a set of images to another set of images. Also, our superglue system only solves the correspondence part. It then uses a classical pose estimation system. What really is necessary is an estimation module to exist inside the network. In addition, the SuperPoint and the superglue system has made matching even more expensive than what you might have been accustomed to. And it has no loop closure mechanism. You will not be able to run superglue on all pairs of collected images, as it's relatively expensive. There needs to be a way to determine very quickly if these two images should be processed by something more complicated or not. That is, I believe keyframe embeddings are necessary to be there to close loops. And keyframe embeddings can be extended with SuperPoint, just another head that creates a single global image level descriptor. In addition, SuperPoint and superglue, those modules, they were separate techniques, and we trained them independently. And I believe in the future, we're going to see more joint end-to-end training. However, I don't think this joint end-to-end training is as important as other people believe. I believe that kind of getting real-world products and getting this out in the world is more important than just having a single train button where everything works magically. And finally, SuperPoint and superglue is the fusion of a convolutional neural network and a graph neural network. The convolutional neural network has its own notion of a receptive field. And then the graph neural network part has a very different notion of the receptive field. I believe more work needs to be done to investigate these two receptive fields working in tandem, as in, how do we have to improve the graph part or the low-level part? So I think that in order to make these techniques sort of work better, we need to have a conversation about which neural architectures give us different receptive fields, and splice together how should they work in unison. So let me finish up by saying some open problems at the intersection of deep learning and SLAM that I believe will continue to drive innovation. If you are a student in this field looking for high-level goals to attain in your research, please listen. First, multi-user SLAM. I believe that creating representations or maps that work across a large number of agents is very important. I think this idea of a single SLAM system is used to build a map, and then it's thrown away, and then a new map is built, has to go away. We need to start thinking about scenarios where person A goes into a room, they build a map, they're effectively done mapping it, and then a second person comes in from a very different door into that room. And they immediately see the space and are able to align what they see with that prior map. In addition, I believe integrating object recognition capabilities into SLAM frontends will be important. I think a real-world product using SLAM will have to do several other things than just the localization and mapping. Getting objects recognized, getting semantics in there is going to be an important future direction. And finally, enabling lifelong learning. letting the system automatically improve over time. My entire adventure in Deep Visual SLAM started with this idea. I really want SLAM systems to go out into the world, perform a task, enable robots to be successful, and then let that data come back in so the machines improve over time. Humans, when they go out into the world, they're able to get better at repeatedly doing similar tasks or even navigating the same environment. I believe we need this property in our system. So to summarize my presentation today, I talked about SuperPoint. These are pretty old ideas now on using convolutional neural networks for replacing the front-end part of SLAM. We saw self-supervised learning, training paradigms using homographies and using visual odometry backends. I also showcased the robustness of SuperPoint and its sister method ChirukoNet and its ability to see in the dark. I discussed superglue, and I do believe it has that amazing success because of the graph neural networks and their newer notion of receptive field. It works extremely well on wide baseline image matching problems. And then finally, I discussed some ideas for how to go beyond pairwise matching on what needs to be done to get end-to-end SLAM working. Superglue will be discussed tomorrow at this workshop by Paul-Edouard Sarlin. In addition, on Friday, at the Image Matching Local Features and Beyond workshop, Paul will also be there to defend the winning entry of using superglue. For those of you that are interested in learning more about our superglue method, there are multiple opportunities this week to come and learn. There will be 2 short presentations tomorrow at this workshop. There will be the main CVPR oral presentation on Wednesday, as well on the last day at the Friday workshop at the image matching workshop. Finally, this is my last slide, and I want to thank everybody for your attention, for coming in here today, checking out our great talks today. And with that, I'm here to take any questions that you might have. Thank you very much.
Thank you, Tomasz, for this great talk. So we have some questions from the audience collected from YouTube. There is a number of questions related to the invariance of SuperPoint and superglue. When you sort of train it or you achieve some robustness, but you do not explicitly address the rotation or more significant scale problems. Do you have any ideas how to do it, whether also the spatial transformer could be used in this case?
Yeah, I think this is a really good question. And I want to point out here is that we train our method to be robust to these transformations. It's not really invariant as in a mathematical property. You can even play with the systems and break them on extreme rotation. So we strive for invariance, but all we really get is robustness. We've really found that heavy data augmentation makes things work better. I do think we need to have a discussion and think about the representations. If we're training everything with extreme data augmentation, maybe something's wrong with how we're training in general. The fact that if you have 10 images, it's better to heavily manipulate them than just train on those 10, suggests that long-term, this might be an issue. We can't just data augment everything. But I think as of today, that is still the key secret. I think you want to do the data augmentation that is more aggressive than what you're accustomed to. Generally, I found that adding extreme noise to the images, making them extremely difficult and dark during training is very important if you're then going to just be able to take the demo out any time of day and have it not break on you.
Okay, thank you. And similar, but related question on superglue, actually, how far you can go in terms of wide baseline? Because we know that something that is not too far from homography can be handled well, I think. But if we start to have close objects that with extreme camera position change significantly the location of points, everything so gets mixed a lot. So how do you deal with that?
I think you can go with superglue significantly farther than you could with SuperPoint. And that's why I really encourage everybody to just get the code up and running and just see it for yourself. But it's still not big enough. There are still examples of images I can create where a human would say, well, that's clearly you just rotated a little bit and you moved a little bit. There's still ample images that I could find that superglue does not work on. The reason is because it still uses SuperPoint. It inherited some of the mistakes of the earlier system. And in addition, during training, and we train on ScanNet and we train on sequences where there isn't as much variation as we would like. I really wish there was a data set that would have the same physical building remapped, once a week for a year. And then you could see the variations across the days. We don't quite have that. So while superglue continues to impress me, I can just as easily break it and bring tears to my eyes and say, SLAM is still years sort of away. It's a little bit of both. I have to say that playing with it is really just the best way to see what happens. But look, extreme scale, extreme rotation, I have not seen anything work in those cases yet.
Thank you. And one more question about the training process. So you do use a lot of homographies and synthetic data in this. Have you noticed actually any significant difference if you start using 3D data, like the points that have really low projection error that you can get from 3D?
So when dealing with the reconstruction part, or when you have the 3D data, suddenly things can go wrong in that procedure. The reason why the earlier training worked well is because we kind of trained on a surrogate problem. COCO and homographies is not quite what we want, but we could do it at scale, a much larger scale than previously we had from any labeled data set. So I think what really we want to do is in practice is use our best SLAM techniques to create an offline SLAM system that can then be used to reconstruct sequences. That is effectively treated as ground truth, and then everything repeats. That's also how ScanNet was created, how a lot of data sets are created. There is a system used sort of in the loop. So maybe the way to kind of move forward is to just keep making better SLAM systems that can be used to supervise the next generation after it.
Okay, thank you. There are, I think, more questions on YouTube, and we probably should invite all the speakers also to check. Maybe they can directly answer there to all audience. So thank you again for a great talk. Let me clap for everyone. And then I hand over to our host, Wenshan, to present the contribution papers.